friends, welcome back to my channel, and today we will be discussing the formal definition of a finite automata or the mathematical definition of a finite automata. Okay, so first of all, let us try to understand why do we need even a mathematical definition of a finite state machine when intuitive understanding of finite state machine is quite easier to understand. Okay, so first of all, let us see what is the mathematically how we represent a finite automata, and then I will tell you why do we need a mathematical theoretic definition of a finite automata. Okay, so finite automata. I am writing in short form FA is a five tuple. Okay, it is a five tuple, and I will write it in a separate color. That is the symbols. Any finite automata is represented using five tuple, using five data pieces of information, or represented as a five tuple. Okay, Q, sigma, delta, Q naught, and F. Okay, this is a mathematical definition of a finite automata. And what is Q? Q is a finite set of states. Finite set of states that the machine can go in. Sigma is set of input alphabet, set of input. Input I'm written in short form as IP, alphabets. Okay. Then transition function sigma. Okay, this is the transition function, and transition function mean how you what is what inputs will be taken for the current state that will be transformed into the next state. Okay, the input is a Cartesian product of possible set of states cross an input alphabet. Okay, means, okay, we will see an example of what this means, and it will give as an output. This is the domain. The input is a Cartesian product, means a set of two tuples which consist of a current state and the current input symbol, and it will give just one next state. Okay, and next is your Q naught is a initial state. Okay, or the start state, and F is a subset. Okay, a subset of Q, and this is a set of accept state, set of final or accept state, final or accept state. Now let us try to understand why we are representing a finite state machine as a set of five pieces of information when intuitively it is far easier to understand what is a finite automata. Okay, so now if somebody wants to understand when what are the necessary conditions for a machine to be a finite automata, whether in a finite automata the set of final states can be empty. That means, can we have a valid finite automata that has no accept state? No accept state. Okay. And this is the first question. Is a finite machine having absolutely no accept state, is it coming under the definition of a finite state machine? And next the question is about, these are the doubts that a person can have, right? And the mathematical definition makes the definition of, or what is a finite automata, when is a finite automata, crystal clear, no doubts at all. Okay, so for in a finite automata, the transition function, um, it takes a single current state, a single input symbol. So for every input symbol on a current state, there can be exactly one next state. There cannot be multiple next states. Okay, this definition is making it very clear. For current state, every input symbol, there can be only one next state. Okay, not two or three next states. Okay, so this is why the mathematical definition is important, that makes it crystal clear of which machines are finite automata and what things are necessary in a finite automata. For example, a finite automata cannot have an empty start state. Okay, so we can see the example of for this machine M1, how can we represent it in the formal way. Okay, so if we want to, the formal definition, formal representation of finite automata M1 that we saw in a previous video in this series. I will give the link of that video in the I tab above. You can check out if you have not seen that. Okay. Now, if we want to represent this formally, so our I will erase the coding part, okay, which we used for coding, the notations. This we used for coding, okay. All right. So it has three set of states, right? Q1, Q2, Q3. So always in this five tuple, the first is the Q symbol. Always the first set would be the set of finite states, okay? So our Q is 3, Q1, Q2, Q3. Always, whenever in a mathematics textbook, you will see a finite automata, the order in the tuple will be this one, same order. Okay, then set of input symbols are 1 and 0. Sigma is 1 0, and uh, the transition table we have to make for this. Okay, so this was the transition table. Okay, it was q1 over here, q2 and q3. 0, 1 and 2 we represented it for Python code for this machine. Now we will write it like, in mathematics we will write it like q1, q2, q3, and this also we will write in terms of q1, right? So this also we will write q1, q2, q3, q2, q2, q2. Okay, uh, transition table, this would be, this only is the transition table. Okay, um, okay, this is the transition function. Okay, and this we have written already. The start state is q1. Okay, and fifth, this is the first information, second, third, fourth and fifth was the set of final states, that is q2. Okay, this is the formal representation of the finite automata M, which we saw in the M1, which we saw in the, as an example in the previous videos. Okay, now let us try to understand this notation. If in a textbook you see, um, in textbooks you will be seeing what this machine M1 does. Okay, what does this compute? Okay, that would be written like this: L of M1 is equal to A. What does this mean? So in whatever strings this machine M1, it accepts means it reaches ends in the final state q2. So whatever strings this machine M1 accepts, those set of strings, it create a set A called the language accepted this by this machine. So the set A inside which all the strings are mentioned which are accepted by this machine M1, or they at the end of the input they reach the final state q2, uh, that is represented as language recognized by the machine M1. Okay, or language accepted by M1, the whole set of strings, that is the language. Okay. So for this machine, I told you before only, it is accepting all the strings which are ending at 1, or after the last one, it is ending with even number of zeros. So if we write formally, the language accepted by machine M1 would be all the strings such that W contains at least at least one 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 and even number of zeros following last one. Okay, so okay, yes, okay. So this is the language that is accepted or recognized by this machine M1. Hope you understood between the difference between strings and the language. Okay. Always any finite automata accepts only one language. Okay. Finite automata accepts only one language. Language mean all the strings which are accepted by this finite automata. But it can accept a multiple strings, but it recognizes only one language. Okay. So if a machine accepts no string, that means suppose there is a finite automata that has no accept states. Okay, this is example q0 and q1 on input uh, 1 and 0. Okay, and on 0 and 1 it is staying over here, but see here there are no final states. So that means uh, the set of strings that is accepted, I am naming this machine M2, the set of languages that is accepted by M2 is 1, and that is the empty. No strings are accepted, so the language is still 1, recognized by M2 is 1, that is the empty language. Okay, so that's it for today. Hope you like this video. Please share it with your friends and subscribe to my channel. Please give your feedback in the comment section below. I would be very happy to know your thoughts, and just be better than you were yesterday. Okay, bye bye. Take care. Happy learning.